Welcome back, students. In this video segment, we will take a look at one section, section 5.4, entitled Eigenvalues and Eigenvectors of Matrices. In this video segment, we're just going to barely scratch the surface of something that's pervasive. It's everywhere in mathematics for the sciences. It's in differential equations. It's in study of linear transformations, in systems of differential equations or systems of equations. It's all over the place. So, without further ado, let's get started. We'll start with a definition. Okay, and then we'll tear apart the definition. So if A is an n by n matrix, so we're starting with a square matrix. So the concept of eigenvalues and eigenvectors with regard to matrices start out with a square matrix. It's given. An eigenvector of A is a non-zero column vector from Rn, such that if you take the matrix and multiply it by the eigenvector, you end up getting just a scalar multiple of the original vector. Okay, so take a look at this equation real carefully here. On the left-hand side, we have a matrix, an n by n matrix multiplied by a column vector. So when you do that, you're going to get a column vector. And there are special vectors, column vectors, such that when you multiply the given matrix by the column vector, you end up with just a scalar multiple of the original vector. Okay, seems kind of strange, but like I said, this concept is all over the place in the math for sciences. And again, the scalar is designated by lambda. Lambda is some scalar, and lambda doesn't have to be real. Lambda could be a complex number. The scalar is called an eigenvalue of A. The scalar is called an eigenvalue. So before we get really deep into how to find eigenvalues and eigenvectors, let's take a look at a simple example to illustrate the definition. So let's let A be the 2 by 2 matrix whose rows are 1, -3, and -2 and 2. And just for your information, I'm going to stay real close to the textbook on this section, unlike 5.3, where I rearranged the topics to make them a little more understandable. I'm going to stay real close. I'm going to expand upon his examples and fill in the gaps where he doesn't explain some specifics. So let's let A be the 2 by 2 matrix, 1, -3, -2, and 2, and let's let V be the 2 by 1 matrix, -1, 1. Okay. Now, if we take A and multiply by V, that means we have 1, -3, matrix A, -2 and 2, multiplied by -1 and 1. Okay. See some words popping up there. I've got some stuff ahead of time. Wrote some stuff ahead of time. Okay, so if we multiply these two matrices, or this matrix times a column vector, we get -4, the column vector, -4, and +4. Okay, so from that result, from that -4, +4, I can factor out using my scalar multiplication of ordinary scalar multiplication of matrices. I can factor out the 4. And look what I get. I took A and multiplied it by some column vector V, and I got a scalar multiple of the original column vector. This doesn't always happen. But when it does, we have something special. Okay, lambda equals 4 is called an eigenvalue. Of the matrix A, and V, the original V we started out with, is called an eigenvector. of A. Okay, so just so we're, again, just to make sure we're all on the same page here, we're given a matrix A. We're given a matrix, and it's a square matrix. And we're not given V or lambda, but when we find V, and we multiply A times V, and we end up getting almost the original V again, but maybe just, not maybe just, but just differing by a scalar multiple, we have an eigenvalue and eigenvector situation. The vector V is called an eigenvalue. The particular scalar is called an eigen. Sorry, I might have said this wrong. The vector V is called an eigenvector, and the scalar is called the eigenvalue. Okay, all right. So the big question: how to find eigenvalues and eigenvectors. Okay, I started out a sentence here, and we'll continue with it. If lambda is an eigenvalue of an n by n matrix A, then the eigenvectors of A associated with lambda are the non-zero solutions to the equation A times x equals lambda x. Okay, so you notice the difference here. I'm writing these capital X's instead of V's on purpose, because what we have here is a system of equations, and we're used to, from our chapter 1, seeing not the letter V or the variable V used for systems, but the capital X, although it's just fine to use V. Okay, now I'm going to rewrite this system of equations. Okay, keep in mind A is an n by n matrix. Keep in mind A is an n by n matrix, and X is a column vector, n by 1 column vector. So we do have on the left-hand side a formation of a system of equations. On the right-hand side, we just have another n by 1 scalar multiple of the same n by 1 column vector. And X is variable. We're looking for X. So if lambda is an eigenvalue of an n by n matrix A, then the eigenvectors of A associated with lambda are the non-zero solutions. And notice I keep saying non-zero. The eigenvectors are strictly non-zero. They're non-zero solutions to the corresponding system of equations. So I'm going to rewrite that system. Because I'd like to find out how to first find not the solution to the system, but to find the actual eigenvalue. So I'm going to subtract lambda x from both sides. And if I do that, I get ax minus lambda x. In fact, I think I'm going to do this a little better. I'm going to subtract ax from both sides. Same thing, same difference. So I'm going to get lambda x minus ax equals the zero vector, zero column vector. Okay. Now, this equation looks like I can factor out an x, but I can't quite factor it out yet. You see, lambda is a scalar, so I can't factor x out of this directly. But I can turn that scalar lambda into a vector, sort of, by introducing the identity matrix. Okay, and then I can group the lambda and the A together, or lambda and the identity matrix together. Remember, we can associate matrices with parentheses and scalars this way, because we have all of our matrix arithmetic from before. Now I can factor out the column vector x. So I'm going to have x. In fact, I'm going to factor it out on the other side. I'm going to factor out the column vector x on the right-hand side. And now I'm looking at a homogeneous system of equations with a really, really fancy coefficient matrix. lambda I minus A. This is sort of like writing the system of equations Bx equals 0, where the coefficient matrix is lambda A minus I. Okay, so what I have here is a homogeneous n by n system of equations. Okay, so I'm going to write that here. I have a homogeneous n by n system. Now, can you think of something associated with the homogeneous system and the solutions to the homogeneous system? Can you think about a way to determine whether or not we have non-trivial solutions? Okay, and what is that connected with? It's connected with the determinant of the coefficients. So, and this is a big part of our lecture right here. The system always has a solution, has a trivial solution, but we're not interested. Remember, we're looking for non-zero solutions. The system has non-trivial solutions, has non-trivial solutions. That means non-zero solutions. If and only if the determinant of the coefficients is what? Is it 0 or is it not 0? The determinant of lambda I minus A is 0. Remember, we get a unique solution, which would be the trivial solution for a homogeneous system. We get a unique solution if and only if the determinant is not 0. We're interested in non-trivial solutions, so we need the determinant of lambda I minus A to be 0 to guarantee the existence of eigenvalues and eigenvectors. Okay, so, and that's stated in theorem 5.16 in your text. We basically just derived it. Theorem 5.16 from our text starts out like this. It says, let A be an n by n matrix. So let A be a square matrix. Lambda is an eigenvalue, if and only if, eigenvalue of A, if and only if and only if, and this is kind of revealing the method by which we find the eigenvalues. If and only if the determinant of lambda I minus A equals 0. Okay, this equation is called the characteristic equation. It's called a characteristic. This is not the first time you've heard of a characteristic equation. Like in chapter 4, we had characteristic equations. Very similar, very similar concept. The characteristic equation, and this determinant turns out to be a polynomial. A polynomial. So it's either called a characteristic equation or the characteristic. The determinant itself is called. I should be careful here. I should be real careful. I'm going to get sloppy with the notation here, or the concepts. Oops. Gosh, I keep messing up here. The determinant itself is called a characteristic polynomial. Sorry about that. Characteristic polynomial. Okay. So let's do this. Let's practice finding the eigenvalues of a matrix. So, for example, find the eigenvalues of the matrix A equals the same matrix we started out with. we observed that an eigenvalue was I think it was 4, but it didn't illustrate how we find it. Okay, so how do we find the eigenvalues of a given matrix? We set up the characteristic equation, and that is the determinant of lambda I minus a. So let's do that. We want the determinant of lambda I minus a. Well, that's nothing more than the determinant of what is lambda times the 2 by 2 identity matrix. It's simply the 2 by 2 matrix with lambda along the main diagonal. So there's lambda I minus, I'm literally plugging in the matrix A now. Oops. I'm going to plug in the right matrix A. Okay. I'm going to simplify that quantity. So we're looking at the determinant of lambda minus 1, 0 minus negative 3, 0 minus negative 2, and lambda minus 2. Okay, and we don't need to look at any fancy cofactor expansions here because it's a 2 by 2 in this case. We're going to get little larger matrices coming up. But this one's simple. Cross multiply, minus 2 times 3, and we set this equal to 0. The characteristic equation says the determinant of lambda I minus a equals 0. And you notice that I mentioned that the determinant of lambda I minus a, that's a polynomial. And you can see that when we multiply lambda minus 1 times lambda minus 2 and subtract 6, we're going to get a quadratic polynomial. So let's just do that. So we get lambda squared minus 3 lambda plus 2, and then minus 6 equals 0. Or lambda squared minus 3 lambda minus 4 equals 0. It's not always the case that we can factor these, but in this case it is, this one. So we get lambda minus 4 times lambda plus 1. I think that works out. Yeah, so we get 2 eigenvalues. Lambda equals 4 and lambda equals negative 1. So now we get the idea of how to find eigenvalues. So how do we find the corresponding vectors v, the eigenvectors? So let's take a look at that. So now on to the eigenvectors, Okay, so if lambda is an eigenvalue of A, and we have 2 of them for our current matrix. In the last example, we have 4 and negative 1. If lambda is an eigenvalue of A, then the eigenvectors of A are the non-trivial solutions to lambda I minus A as a coefficient x equals 0. Okay, so that tells us what we need to do. Now we have some terminology associated with this idea. So recall that these things we call the solutions, or the eigenvectors, they, along with the non-trivial solutions, form what's called the null space of this matrix lambda I minus a. Remember, the null space of a matrix, of a square matrix, is the set of solutions, including the trivial solution, to the homogeneous system AX equals 0. Okay, so we're finding the null space of this new lambda I minus a. And the null space, remember, the null space is a subspace of of Rn. So we call this null space the eigenspace. We're going to get some fancy terminology of lambda, or E sub lambda. So lambda is an eigenvalue. We want the eigenvectors. The eigenvectors are the null space of the lambda I minus a. And the null space is a vector space itself. It's a subspace of Rn. So we call that space that's related only to the particular eigenvalue lambda. We call that E sub lambda. Last note before we dig in, we've done this before. We found the basis for a null space. We've done this before. So we're not doing mechanically, we're not doing anything new. We just have a new concept that we're applying our old mechanics from section 2 to do. Okay, so for example, basically going to expand upon our last example. Find the eigenvectors of the original matrix in the last example, A, whose columns are 1, -3, and -2 and 2. Okay, so we have two eigenvalues, 4, lambda equals 4, and lambda equals -1. Let's do them one at a time. Lambda equals 4. Okay, I need the non-zero, non-trivial, the non-zero solutions now to lambda I minus a times x equals 0, or lambda 4I minus a x, the unknown column vectors, equals 0. Those column vectors in that system, those are the eigenvectors. Okay, so let's find 4I minus a. Okay, well, 4I minus a, 4 times I is the diagonal matrix whose entries are 4 and 4, minus a, 1, -3, -2, and 2. I'm just looking at the coefficient matrix of the system now. Okay, and this is nothing more than 3, 3, 2, and 2. So that's the coefficient matrix of the object of our affections, the system 4I minus a x equals 0. Okay, so now we're going to solve 4I minus a x equals 0. So what we're going to do is we're going to set up the augmented matrix for the system, which is 3, 3, 0, 2, 2, and 0. Okay, and then we find the RREF. And we get 1, 1, 0, 0, 0, 0. Okay, so this is the RREF. What does that tell us? It tells us that x plus y, if we assume that our eigenvectors are of the form column vectors x, y, we get x plus y equals 0. Okay, well, we have a row of 0, so that indicates we have a free variable for y. Okay, so this says that xy equals, well, if x plus y equals 0, that says that x equals -y. So x equals -y, and y is the free variable. Those are our eigenvectors, where y can range through all real numbers. I can factor out the y, and I'm looking at, and I want you to listen carefully here, I'm looking at my eigenvectors are nothing more than a scalar multiple, scalar multiples of the column vector 1, -1. Okay. Okay, so that tells me that the basis for the eigenspace of the eigenvalue 4, that's E sub 4, is -1 and 1. Well, if you're thinking if you want to think back, how do we form a basis? We need linear independence and spanning. Well, we have the spanning. The vector xy is a linear combination of one vector. And one vector is, as long as it's not the zero vector, is always linear independent. The only solution to the equation C1 times negative 1, 1 is a column vector equals 0, C1 equals 0. So this is, in fact, a basis. Okay. Well, the question said, what are the eigenvectors? Well, the eigenvectors are nothing more than y times that vector, or if you want, you can use c times negative 1, 1. So this matrix has an infinite number of eigenvectors. Anything of the form c times negative 1, 1 is an eigenvalue. Okay. We have one more eigenvector value rather. Lambda equals negative 1. So we're going to do the same thing. Okay. We need to solve lambda I minus x, so lambda negative 1 times I, lambda I not minus x, lambda I minus a times x equals 0. Okay, so we're going to need lambda I minus x. So negative 1 times, I guess we can just do it here. So, okay, negative 1i minus a is, well, negative 1i is the column, 2 by 2 column matrix, diagonal matrix rather. These entries are negative 1 and 1. That's negative 1 times I minus the original a, 1, negative 3, negative 2, and 2. And this is nothing more than negative 2, 3, 2, and negative 1 take away 2, negative 3. Okay, so now we're going to solve the system. Negative 1i minus a times x equals 0. So we augment the matrix, negative 1i minus a, and then put as the constants the 0 column vector. And that gives us nothing more than negative 2, 3, 0, 2, negative 3, and 0. We find the RREF. And that turns out to be, let's see, I did it for us here, 1, negative 3 halves, 0, 0, 0, and 0. Okay, so that tells us that x minus 3 halves y can equal 0, where y can be any real number. So x equals 3 halves y. And that gives us that our eigenvectors now look like 3 halves y, comma, not comma, column vector y, factor out the constant y. Remember, y varies through real numbers, so our, oops, that's why I put it back in there again. Y varies through real numbers, so our eigenvectors are multiples of, scalar multiples of the column vector 3 halves and 0. 3 halves and 1. Oh my goodness. That was a really very bad mistake. Okay. Okay, so a basis for the eigenspace of negative 1, I think that was our eigenvalue was negative 1, is 3 halves and 1. Now I'm going to write something here in red, or I want you to think about why this is also true. 3 and 2. Okay. The reason why we could use 3 and 2 instead of 3 halves and 1 is because my eigen vectors are linear combinations of one vector. They're scalar multiples of this one vector. Well, scalar multiples of 3 halves and 1 are the same as scalar multiples of 3, 2. You can multiply the column vector 3 halves and 1 by 2, and you can obtain scalar multiples of either by using either of the vectors. Okay, so if in other words, that didn't turn out too well, that last statement. The scalar multiples of 3 and 3, 2 are the same as the scalar multiples of 3 halves and 1. So if our eigenspace is formed by the eigenvector by scalar multiples of 3 halves and 1, then certainly they're the same as the scalar multiples of 2 times 3 halves and 1, or 3 and 2. Okay. So the eigenvectors, well, this is very easy now. So the eigenvectors, the actual eigenvectors in our space, eigenvectors are C times either 3 halves and 1, or C times 3, 2. Okay, either is just fine. You think your author in the solutions to homework problems, I think he clears fractions and stuff most of the time, if not all the time. Okay, let's do this for a more complicated case. Let's take a look at a case where we're trying to find the eigenvalues and, let's say, basis for the eigenspaces for a larger matrix. So let's do that. So find the eigenvalues. Let's see, and let's say bases for the eigenspaces of the matrix A equals and -6, -4, and 4, 0, 2, and 0, -8, -4, and 6. Okay. So the two-step process is going to make it sound real simple here. But it really is conceptually pretty simple. The first step is you find the eigenvalues. You find the determinant of lambda I minus a, set that at equal to 0 to find the characteristic equation. Solve the characteristic equation. Then you go eigenvalue by eigenvalue and find the corresponding eigenvector. So let's find the determinant of lambda I minus a. Okay, that's the same thing as the determinant of lambda times the 3 by 3 identity matrix is the diagonal matrix whose entries are all lambda, 3 by 3 of course, minus, here's our A, 4 and 6. Take a real quick look to make sure, I'm taking a quick look back just to make sure I copied that matrix right. Yeah, okay. So this is, now it gets a little more complicated than before. This is lambda plus 6. Let's go look along the diagonal first. Lambda plus 6, lambda minus 2, and lambda minus 6, and minus the values of a. So let's see, 4, -4, 0, zeros, 8, and 4. I'm trying to be real careful here. This is where I tend to make mistakes, and there's a lot of numbers floating around. Okay, I need the determinant of this matrix. Well, things suddenly got a little more complicated than before. We have a 3 by 3 matrix, but we don't have to expand along the first row. So I'm going to expand along, what do you think? Not the first row, not the second or third row. I'm going to expand along the second column. Okay, so if I expand along the side, I'm going to write that in so if you look back here. So I'm going to expand along column 2. I only have one non-zero entry there. Okay, so it's going to be, let's see, lambda minus 2 times negative 1 to the 2 plus 2. I'm going to use some jargon that we haven't seen in a while, times the determinant of the 2 minor of this matrix. Okay, it's basically the determinant of the matrix you get by eliminating the second row and second column. So let me do that here. It's been a long time since we looked at a determinant. Expanding one by hand here. Okay, so this determinant isn't too bad. So we have lambda minus 2, negative 1 to the 2 plus 2 is just 1, times this determinant has a 2 by 2 determinant now. A determinant of a 2 by 2 matrix is just lambda plus 6 times lambda minus 6. And then cross multiply upwards, so minus negative 4 times 8, so plus 32. Okay, we're getting there. Lambda minus 2 times lambda squared minus 36 plus 32, or lambda minus 2 times lambda squared minus 4, or continue to factor lambda minus 2 again, lambda plus 2. So we have a 0 of multiplicity 2. So we set this equal to 0. Oops. We set this equal to 0. That's our auxiliary equation. So we get lambda equals 2, a 0 of multiplicity 2, and lambda equals negative 2. Okay, so that's the first step. Find the eigenvalues. The next step is to solve for the eigenvectors that correspond to the particular eigenvalues. So let's handle them one at a time. The order in which you handle them is not important. So let's take negative 2 first. So we're going to solve now the system of equations lambda, negative 2, I, minus a x, ugliest looking x I've written today, capital X equals 0. It's not much better. Okay. Well, in order to do this, we're going to need the coefficient matrix, negative 2i minus a. Just the coefficient matrix for now. And what is that? It is, well, negative 2i, negative 2 along diagonal, zeros everywhere else, minus the original a, negative 6, negative 4, 4, column 0, 2, 0, third column, negative 8, negative 4, 0. Make that a little better looking. Negative 6. Okay. So we end up with 4, 4, negative 4 for the first column. For the second column, we have 0, negative 4, and 0. For the third column, we have 8, 4, and negative 8. Okay, so there's our coefficient matrix to solve for the eigenvectors corresponding to the eigenvalue, negative 2. Just taking a real quick look to make sure I didn't make any mistakes. I think it's okay. So here's what we do. We use the Gauss-Jordan elimination method to solve the system of equations, negative 2i minus ax equals 0. So we augment with the 3 by 1 column vector, 0 vector, and 4, 4, negative 4, 0, negative 4, 0, 8, 4, negative 8, zeros, find RREF. The RREF turns out to be, we don't need to look at the mechanics. You can always use your calculator to find the RREF of a lot of these matrices, and that's a kind of a scary thing I just said there. With some of these matrices we're not going to be able to do it. We'll see why. A couple of seconds. A couple of minutes. All right, so here's the RREF for our particular system. And what that translates into is x plus 2z equals 0, y plus z equals 0, and we have as a free variable z. Z can be any real number. Okay, let me clean up that last z. It doesn't look like that. Neither of those z's look like z's. 2z and z. Okay, so this tells us that x equals negative 2z, y equals negative z, and z is the free variable. So our eigenvectors look like x, y, z. These are those v's that we started out in our original eigenvalue, eigenvector problem. They look like negative 2z, negative z, and z. Again, we are looking at scalar multiples of just one vector, so we automatically get linear independence with one non-zero vector. Okay, so the basis for the eigenspace corresponding to the eigenvector negative 2, so E sub negative 2 is simply the vector negative 2, negative 1, 1. Any non-zero multiple of this one column vector is going to be an eigenvector. Okay, I know it's tedious. Well, we're going to look at the second one. You can always, after you view this once, you could skip through the second eigenvalue. It's exactly the same. Or I don't recommend you skip through it now. I think you should watch it. But we're going to do the same thing with lambda equals 2. I think our first eigenvalue was negative 2. Second is eigen 2. So we are going to solve. We are going to solve 2I minus a x equals 0. Those x's, capital X's in this equation, those are my eigenvectors. So we're going to need 2I minus a as a coefficient vector, a matrix rather. So 2I is a diagonal matrix. 2's everywhere along the diagonal, 0's everywhere else. Sloppy, sloppy, sloppy. Okay, so there's 2I minus the original, same old a, negative 6, negative 4. I've almost got this matrix memorized. 0, 2, 0, and 0 looks like a 6. Let's not have it look like a 6. And negative 8, negative 4, 6. Positive 6. When we subtract these two matrices, what we get? 8, 4, negative 4, and 0, 0, 0. And 8, 4, negative 4. Okay, I'm literally checking every computation twice here to make sure this is okay, because I don't want to edit a video. Okay, all right. So we augment 2I minus a with the 3 by 1 0 matrix, the column vector. Okay, to get, this is like completely trivial here to write. 0, 0, 0, just takes a lot of writing here. Augment it. Okay, RREF by our calculator. And what do we get? We get 1, 0, 1, 0. And we get zeros everywhere else. Okay. So this tells us that x plus z equals 0. And what else does it tell us? It tells us we have two free variables. It says that y and z are both free variables. Okay, so we can write that in, I guess. We just say y equals y and z equals z. That's really common to do. Okay, where y and z are both real numbers. So what do our vectors look like? They look like x, y, z equal. Well, the first equation tells us x equals negative z. Y is a free variable and z is a free variable. Okay, well, we're getting a slightly more complicated set of eigenvectors for this particular eigenvalue. Okay, so we can tear this eigenvector, or this set of eigenvectors, apart by looking at, let's write the so how do I want to do this? Okay, I'll write this as 0, y, and 0 plus, just using the definition of our addition and scalar multiplication for this vector space, R3. I can factor out the y. 0, 1, 0. We've done this before. We've done this. If this looks familiar, we've done this sort of thing before in chapter 2, chapter 2.4, I guess. Okay, so our eigenvectors are linear combinations of these two vectors. The two vectors then form a spanning set for the set of eigenvectors. But these vectors are linearly independent because they're not proportional. I hope this is sounding familiar. So the basis for the eigenspace corresponding to the eigenvector 2 is going to be the spanning set 0, 1, 0 and 1, 0, 1. They are linearly independent since they are not proportional. One is not a scalar multiple of the other. Or no. We didn't have to do that in the last eigenvalue because we only got one basis vector. Okay, so this is a basis vector for E sub 2, or the eigenspace corresponding to the eigenvector 2. Okay. So now we're going to change things up a little. We're going to go to another 2 by 2 matrix, but the eigenvalues turn out to be a little different. So here's our problem. Determine the eigenvalues and eigenvectors of the 2 by 2 matrix whose rows are 1, negative 1, and 1, 1. So the first thing we're going to do is we're going to set up the characteristic equation. So characteristic equation to find the eigenvalues. Okay, so the characteristic equation is the determinant of lambda I minus A equals 0. And let's figure out the left-hand side first. So it's the determinant of lambda I, or will be the 2 by 2 diagonal matrix, lambda's along the main diagonal, zeros everywhere else, minus A. At least you won't have to watch me rewrite that matrix, the 3 by 3 matrix, over and over and over again. So equals the determinant of lambda minus 1 and another lambda minus 1 along the diagonal, and negative 1 and positive 1. Oops, I don't need to load a plus there, just 1 for the other entries. And we set this equal to 0. Okay, so let's do this determinant. Let's perform this determinant. It's lambda minus 1 times lambda minus 1 is determinant of a 2 by 2 matrix, real simple, plus 1 equals 0. We get lambda squared minus 2 lambda, lambda squared minus 2 lambda plus 1, plus another 1 equals 0. And we get lambda squared minus 2 lambda plus 2 equals 0. Now this isn't going to factor. Well, I guess every quadratic factors. It's just not going to factor with real nice numbers. So we'll use a quadratic formula. So lambda equals negative b plus or minus the square root of b squared. So b squared, b is negative 2, so b squared is 4. Minus 4 times a times c. 4 times 1 times 2 is 8. So there's where the problem starts. We have underneath the square root side, we have the discriminant. We call that as negative. So our eigenvalues are complex. Okay, that presents a little bit of a problem. So we get complex valued eigenvalues. Okay, but the method doesn't change. We do have some light at the end of this tunnel, though, with complex valued eigenvalues. It's really, really nice toward the end here. For now, let's just dig in. We have lambda equals, let's say 1 plus I. Let's find the corresponding eigenvectors. So we're going to solve 1 plus I times capital I minus A, all of that times x equals 0. Okay, so this is where we have to do some work by hand. The reason for that is our graphing calculators don't work with complex numbers. At least the TI-84 doesn't. I'm not sure about Inspire and the others. Okay, so let's see. 1 plus I times the identity matrix A. Let's identify that coefficient matrix is 1 plus I times the 2 by 2 identity matrix is the diagonal matrix, whose diagonal entries are 1 plus I, zeros of course everywhere else, minus our original A, 1, negative 1, 1, 1. Okay. So the net result here is 1 plus I minus 1 is I. So we're going to get I, 1, and negative 1, and I. Okay. So let's solve the system. Let's augment the matrix. Let's augment the matrix 1 plus I, capital I, minus A, with the 2 by 1, 0 vector. And that gives us, I want a little more room here. I wonder if I'm going to be able to slit more room in here. Sorry about that. Give me a second here. I can. Okay, so I just want a little more room. So that gives me I, 1, 0. And it also gives me negative 1, I, and 0. All right, so we need to do some row reducing on this. I want 0 is the first entry in the second row. Okay, so I'm gonna, I have to remember a couple of things here. First of all, I squared equals negative 1. We'll need that in a little bit. But I want a 0 in the second row in the first column. So that's not so bad. All I need to do is take I times row 2 and add that to row 1. If I take I times row 2, I'll get negative I in the second row and first column. And I add that to the first row and first column. Negative I plus I is 0. So that works out not too bad. So I have I, 1, and 0. So the first row is not being affected. So I times row 2 plus row 1, 0. I times I is I squared, or negative 1, plus 1 is 0. And any multiple, 0 plus 0 is 0. So this isn't so bad. Okay, well, I have one more step for the reduced row echelon form. I want to produce 1 in the first row and the first column. So I'm not going to multiply by I. I'm going to multiply by negative I. I'm going to multiply the first row by negative I, and then put that back. Remember, I squared is negative 1. So negative I times I is negative I squared, or positive 1. So I'm going to have 1 and negative I, 0, zeros everywhere else. Okay, so our solution then looks like x minus I y equals 0, where the free variable is y. So this says that x equals I times y. Remember, we're looking for eigenvectors. We're looking for the solutions x, y, and they're complex. They have complex entries. The entries are x equals I, y, and y is the free variable, so second entry is y. So our eigenvectors are scalar multiples of the column vector I0, I1. I keep doing that. This is the second time in this lecture I've done that, I1. It's very bizarre. Okay. And it's okay. We just have complex valued eigenvectors. So the basis for the eigenspace corresponding to the vector, the eigenvalue 1 plus I, so E sub 1 plus I is I1. We have linear independence because we have one non-zero vector again. So that leaves us with one more eigenvalue. Okay. And again, remember I promised something nice at the end of this. We have 1 minus I as the second eigenvalue. Now, notice that our eigenvalues are conjugates of one another, and that's going to come into play later. So focus on your screen now. I'm writing in red. We have conjugates as eigenvalues. Okay, and we learned about that back in pre-calc, that when you're solving a polynomial equation and you have a complex valued solution, that the conjugates. Let me state it this way: the complex solutions occur in conjugate pairs. So if you have a plus bi as a solution to a polynomial equation with real coefficients, then a minus bi is also a solution. And the same thing's going to happen with the eigenvalues. Since the eigenvalues are just roots to a polynomial equation, they're going to occur in conjugate pairs. That's not the nice thing. The nice thing comes fairly soon. So let's take a look at going through and finding the eigenvalues or eigenvectors corresponding to 1 minus I. So we're going to solve, not in black, I want to go back to black, or not in red, I want to go back to black. So solve 1 minus I times capital I minus A. That's our coefficient matrix, x equals 0. So I'm going to need 1 minus I times the identity matrix, 2 by 2 identity matrix minus A. So that's nothing more than the diagonal matrix whose entries are 1 minus I minus the original A. Okay, and when we perform this arithmetic, we get negative I, 1. Let's see, what do we get? Negative 1 and negative I. Okay, so we're going to augment the matrix 1 minus I times capital I minus A with the 2 by 1, 0 vector in R2. And that gives us negative I, 1, negative 1, negative I. Tack on the zeros for the constants. And then it brings us to kind of a grinding halt at first. We need to do this work by hand. So let's do that. Let's try to get 0 in the first entry in the second row. So I'm going to take I times row 2. And I'm going to add row 1. Or am I going to add? No, I'm going to subtract row 1. Okay. Subtract row 1. So I'm going to leave row 1 alone. Okay, so I times row 2. I times negative 1 is negative I. Subtract negative I, that gives us 0. So I times negative I is 1. Okay, plus 1, wait, sorry, minus 1 is 0. I'll state that again. I times negative I is negative I squared, or positive 1, minus the 1 that's in row 1 is 0. So we get zeros. We get a 0 row again. And then I'm going to multiply the first row by I. I times row 1 will transform the first row into 1, I, and 0, and then 0 for the second row. Okay, so let's rewrite this system. It is now x plus iy equals 0, where y is the free variable, so x equals negative iy. So our eigenvectors are x and y equal negative iy and y. This time I won't say 0 for the second entry. Y times negative I and 1. I wanted to put a 0 there. That's just so weird. Okay. So a basis for the eigenspace corresponding to our conjugate 1 minus I is negative I and 1. Now what's the positive thing that I wanted to mention here? Recall that the basis for the eigenspace corresponding to the 1 plus I was I and 1. Now notice that the basis for the conjugate is just the conjugate of the matrix for the basis for the original 1 plus I. So the basis for 1 plus I had I and 1. The basis for the conjugate was just the matrix corresponding to the conjugate of the original basis for e sub I plus 1, 1 plus I. I did not come out really well. So I'm going to write something really neat here. Give me a second. So I've got this in better words here. Notice that the entries of the basis vectors for the two eigenspaces e sub 1 plus I and e sub 1 minus I of the individual complex conjugate roots, they're also conjugates of one another. So notice in the column vectors, I and negative I are conjugates, and they correspond to the conjugate roots of the characteristic equation. This is always true. And that brings up our last theorem for this video segment. A little bit of notation. We're using for conjugate a bar over the conjugate, over the complex number. So the conjugate of 3 plus 4i, the conjugate of 3 plus 4i is 3 minus 4i. Very common notation in complex analysis or complex variables to do that. So theorem 5.17 just basically says what I wrote in a sentence. Suppose we start out with a square matrix with real entries, okay? And suppose that we find that lambda equals r is an eigenvalue of A, which could be complex. And let's say it is complex. So lambda equals r is a complex eigenvalue. And that we find that V1 through Vk form a basis for the eigenspace corresponding to R. Then automatically we're going to find that lambda equals the conjugate of R is an eigenvalue. So eigenvalues occur in conjugate pairs, but so do the eigenbasis, the basis for the eigenspace. They occur as conjugate values. So if V1 to Vk formed for a basis for the eigenspace corresponding to R, then the conjugates of those form a basis for the eigenspace corresponding to the conjugate of R. Okay, so back up to our example real quick before we end this segment. In the last example, I started out by finding the two eigenvalues. Okay, 1 plus or minus I, and they were conjugates. And this part of this last theorem says that this is always going to happen. Okay, then, and here's the good part, I found corresponding to the eigenvalue 1 plus I found a particular basis. The basis was the 2 by 1 column vector I and 1. There's no work to do after this. Our last theorem guarantees me that for the other eigenvalue 1 minus I, all I have to do is find the conjugates of the basis vectors for 1 plus I. Okay, so all I would have to do is find the conjugate of I, which is negative I, and the conjugate of a real number is just itself. So all I would have to do is state that the basis for the eigenspace corresponding to 1 minus I is just negative I, the column vector negative I, and 1. Okay, so it shaves off a bunch of work. Okay, so that takes us to the end of section 5.4. Go ahead and dig into homework right away with this while this is fresh in your minds, and I'm looking forward to talking with you again when we hit 5.5 coming up.